Okay, hi everyone. On the way out, Arusha asked me to do the answers from the homework last night that we didn't get to go over in class today, and it was this homework. Page 273, 40, and 26, page 284, 85, 10, and 34. I only did one of these, okay? I don't think I need to do both of them, but here's 26, and the question here, the instructions were to find the x coordinates that correspond to an absolute max and an absolute min value of f of x over this domain. And as you can see here, I started to do the work and then I said, oh wait, duh. It's a polynomial function of odd degree over this interval of all real numbers, and a polynomial function of odd degree has opposite end behaviors, therefore there is no absolute max or absolute min on the interval. Here's number 40. And as you do and I do, as we're all human, whenever there's a closed interval, I always kind of forget about it. Like in my work, I'll just kind of chug along and forget, so I tend to just make a big arrow. But here's f of x, here's me finding f prime, and that little trick I showed you, that's going to be so handy. There's a common factor in these two terms. Factored e to the x out, this is what's left inside. There are no points where f prime is non-existent, so the only critical points would be where f prime equals 0. So here's me setting the derivative equal to 0. E to the x will never equal 0. This is a, look how I reorder the signs here, this is a quadratic expression. And setting that equal to 0, you could use the quadratic formula or completing the square. I would opt for completing the square in this situation, it's easier, but I did the quadratic formula because some of you do that, so I'm going to do it here. If you use the quadratic formula though, look, all of this just simplifying, that makes my life easier. And then I have these two critical points. When f prime equals 0, x is negative 1 plus radical 2, x is negative 1 minus radical 2. This is not in the domain of negative 2 to 2. Only this is in our domain. Here is me doing the first derivative sun analysis. F prime is neg, pause. That means f decreases going to horizontal tangent and then increases. So if f decreases then increases, at this x value an absolute minimum must occur. And here's me writing it out. But it's a closed interval of concern. So if f looks like this, everyone, decreases and increases, both of the endpoints are potential locations of absolute maxima. So I have to compare those two in the original f value to figure out what the y coordinate is. See, calculus just makes so much sense if you just make sure you think about it. F of negative 2, here is me just plugging negative 2 into f, the function. Where is it? Where am I? Right there. And if I do it correctly, and I shall, I get 3 times e to the negative second. Okay? And then f of 2 is 3 times e to the positive second. This is the obviously bigger number, so the absolute max value of f of x occurs at x equals positive 2. Okay? And then I did one of the applied optimization questions here. Right here, find the point P in the first quadrant on the curve y equals x to the negative second, such that a rectangle with sides on the coordinate axes and a vertex at P has the smallest possible perimeter. So here is the thing to be optimized, and here is my totally uncontextualized equation to be optimized. But what's the context? So I just kind of sketched this, sketched the curve, sketched my rectangle, and I thought, oh, yee, interesting. I noticed that for this rectangle, the length just corresponds to like the x coordinate of this point, and the width corresponds to the y coordinate of this point. And even more to the point is the fact that the y coordinate of that point is just 1 over x squared. So now I have my contextualized equation to be optimized, which is here or here. And I just kind of made note of any common sense domain restrictions. Whenever we talk about applied optimization, we always just make note of any kind of common sense domain restrictions. And then I took dp by dx What a great conversation in class today about why it is we take the derivative with respect to x, right? D by d, whatever the independent variable is. And here you see my work going through. I found a point where p prime equals 0, found the second derivative, and noted that the second derivative at this point, and at all points actually, is always positive, which means the p function is concave up, which means we have a minimum perimeter at x equals radical 3 over 2 by the second derivative test for extrema. All right, let me go close the door on the screaming children outside, and I'll be right back. Okay, hi everyone. So I went to close the door because of the noise out in the hallway, and I walk outside, and guess whose voice is the one that's booming? It is our lovely classmate, Daniel. And Daniel, I'm just returning the favor of you very nicely calling Paige the lovely Paige in our class. I just called you the lovely Daniel, the lovely, loud Daniel. Okay, here's some new content, and on nights like tonight, when I know that you will likely be kind of doing some studying, I like to keep it light. This new content is new in terms of an idea, new in terms of some words, but there's actually no new math here, okay? We've done questions like this many, many times, okay? Let's say we have some function, okay, that is continuous on some interval of x from a to b, okay, and also differentiable on the interval of x from a to b. So that's the first condition. There is some function that is continuous and differentiable on some interval from a to b, okay? There is a theorem that almost goes without saying, and it's almost obvious to us because, believe it or not, we've been working with this theorem without even knowing we've been working with this theorem, which is kind of the best way things happen. If there is a function that is continuous and differentiable on some interval a to b, there must be at least one point. That point is referred to often as C. There must be at least one point C between a to b, such that the line tangent to the function is parallel to the line secant to the function. And when I look at my drawing, it's not great because see where this point is. But you get the point, okay? Let's talk about why I emphasize some key words here, and we'll write out what this theorem says in a moment. So no need to write anything down other than just listening to me so far. If you want to draw a picture, you certainly can. And now that I look at this, these two lines aren't even parallel. Oh, Ms. Yam, what's wrong with you? I said that if there is a function that is continuous and differentiable on a to b. Well, let's just talk about the fact that why does the qualification of continuous and differentiable have to be there? Well, let's see. Let's say I have our old friend, the absolute value function, okay? And let's say I pick the point, I don't know, let's say I pick the point -4 and +4. And do you see here that the slope of the line secant to the function, or the slope of this line segment, is 0, right? This theorem would suggest, if it didn't have the precursor or the criteria of the function being continuous and differentiable between -4 and 4, there is no point C between -4 and 4 where the slope of the line tangent to the function is 0. And this point of non-differentiability, the fact that there is a point of non-differentiability on the interval, is what makes the conclusion up here not necessarily the case, okay? And I think I'm just being so clumsy with my words. I could be much more eloquent than this. So in other words, what I'm emphasizing here is the fact that for this generalization, the generalization being, there must be at least one point C such that the slope of the line tangent is equal to the slope of the line secant to a function. Only if, though, that function is continuous and differentiable in a to b. Now you see why, if the function is not differentiable, that result may not be the case. Okay? By similar extension, I mean, what if this had been not continuous, right? Let's just do a simple example of like y equals x squared, but let's say that there's a hole right here. Okay. Oh, even better. Let's do this one. Let's do this curve. I don't know why I've got all these pastels like yelling at me now. I don't like these pastel. Okay. Let's say I've got, let's see, what curve is this one? What curve is this? Our good friend, the what, everyone? Don't say cube root. I mean, don't say cubic until you see me do this. Okay. What curve is this, everyone? What curve is this, everyone? I better say the tangent function. Tangent function. Where do these vertical asymptotes occur, everyone? Pi over 2, negative pi over 2, 3 pi over 2. Okay, and where do we say vertical asymptotes occur at y equals tan x? At pi over 2 plus any multiple of pi, right? All right, so let's say I do this. Let's say I want to look at the interval from pi over 4 to, I don't know, let's say 3 pi over 4. Oh my goodness, I just spat on my, okay, and that's my interval, and my interval is from pi over 4 to negative pi over 4, and what I've got here is, let's see, here is that point, here is this point, and there is the slope of the secant line, okay? And there's a couple things going on. If you look at the tangent function, the tan x function is always an increasing function. When I scan the function left to right, it's always an increasing function. So there is no possible way there'd be a slope of a line tangent to the tangent function when the slope would be negative, as this secant line clearly, secant line slope clearly is. But look at the interval. Between negative pi over 4 and 3 pi over 4, the function is not continuous. Okay, so we can't make the conclusion that there must be at least one point where the line tangent is parallel to the line secant. At least one. What's the big deal with at least one? Why am I making a big deal of at least one? Okay, let's see. Maybe I have a function that looks like this. Okay, and this is my function f of x, and let's say I want to look at this interval from, oh, I don't know, let's call it a to, let's call it a to b. Okay, so from a, whoops, I didn't want it to look like that. Okay, let's do this. Let's erase that. Go back. Okay, a to, woo, let's extend over it. A to b. Okay, and so here are my points. Here are my points, and look at that. There's a slope of the secant line. Oh, and I missed. And when you miss, all you do is just make the dot bigger. And again, over the interval from a to b, clearly you see the function here is continuous and differentiable. And if I ask you to look for the values of c between a and b, so at the x values where the line tangent to the function has the same slope as the secant line, you'd probably be able to eyeball several of them. Like it'd be right here as a point of tangency, right? It'd be right about here as a point of tangency. Maybe right about here as a point of tangency. So there's the at least one. Okay, I've been belaboring so long, but here is the theorem. It is called the mean value theorem. And if you were at a party, everyone knows that that is just the MVT, okay? MVT is the mean value theorem. And here's what the mean value theorem says. It says, if f of x is continuous on some closed interval of a to b and differentiable on that same interval of a to b, but it's open. I'll talk about the distinction in a minute. Then there must be at least one value c such that A is less than C, which is less than B, such that, okay, and here's what it says, such that f of B minus f of A over B minus A equals f prime of C. All right? All we're doing here is putting into words and some math what we just talked about. The reason why we talk about continuity on a closed interval is because if we're looking at endpoints, for example, if we're looking at an interval of here, look at this graph, from A to B, if the curve, if f of x, for example, like had, oh heavens, if f of x had like a hole right here at A, then there couldn't possibly be a secant line because there wouldn't be a point there. So there has to be continuity at the endpoints, okay? Why does differentiability not include the endpoints? And here I'll give you an answer right now that's not going to be very satisfactory. If we're talking about just an endpoint, there is something called one-sided differentiability. You know, so when we talk about a curve of f of x, right, here, and we are looking at just an interval of f of x. Technically, at this point, if we're just looking at an interval, say from A to B, right? At the point, technically you have this, like, you can't have a tangent line. It'd be kind of swinging around and dangling on this, right? Now, I say that, but then I also add the caveat that there is something called one-sided differentiability. The way I get around this is I just say if f of x is continuous and differentiable on the interval of x a to b, then there must be at least one value, and this is just a lot of verbiage, x equals c such that, da-da-da. This is just saying some x value between a and b such that, now look at this. This right here is the slope of the secant line, y1 minus y2 over x1 minus x2. This here is the slope of the tangent line, okay? What I'm going to talk about tomorrow, I'm going to tie this into what these mean in terms of rates of change. What's being described here are two different types of rates of change of x. Of f of x, and we'll talk about that tomorrow. Let me show you what a sample question could look like, okay? And I literally just copy and pasted what the instructions may look like from your text, and you'll see in a minute, okay? So right here, right, it says, verify that the hypotheses of the mean value theorem are satisfied on the given interval, and find all values of c in that interval that satisfy the conclusion of the theorem. The hypotheses of the mean value theorem just means the criteria, like the criteria for the mean value theorem to hold. Those hypotheses are f of x being continuous and differentiable on the interval, right? So here's what we're going to do. Let's just do number 5, I guess, okay? Now, a couple ways you could attack this. You can certainly graph this parabola if you want to, and then kind of look at the interval and say, like, oh, okay, let's graph those points, find the secant line, or you cannot. I'm going to choose not to. I'm first going to make the note to myself and to the reader here that this function is a quadratic function, and a quadratic function and a cubic function, in fact, all polynomial functions are continuous and differentiable for all real numbers. So, ergo, the hypotheses of the MVT are satisfied. I'm now going to go about finding the slope of the secant line, okay, and the slope of the secant line is going to equal f of 5 minus f of negative 3 all over 5 minus negative 3 or 8, okay? When you do that, we get 1, and that's the slope of the secant line. what we have to do is say, let's find the value of x, find a value of x between negative 3 and 5, such that the slope of the tangent line will equal 1. Well, let's see. What is f prime of x going to be? F prime of x equals 2x minus 1. When will 2x minus 1 equal 1? Well, 2x minus 1 will equal 1 at x equals 1. So at x equals 1, f prime of x equals 1, and this equals the slope of the secant line. Okay, and specifically this value of x equals 1, is on the interval, or between negative 3 and 5. Okay, so with this you should be all set to do your homework, and I will see you tomorrow. Goodbye.